Welcome to the 70th Theoretical Physics-Colloquium by Professor Dean Lee from Michigan State University. He got his PhD in 1998 from Harvard University. After that, he had a postdoctoral position at University of Massachusetts Amherst between 1998 and 2001. In 2001, he got a faculty position at North Carolina State University, where he was promoted all the way through the professor. And in 2017, he moved to Michigan State University, where he remains since. He did a lot of work, has a lot of awards and honors. In 2014, as one of the examples, he was elected a fellow of the American Physical Society. The quotation reads, "For the development of lattice-effective theory as a novel approach to the nuclear fuel and many-body problem, and for applications of this technique to the structure of whole state." He also is active in professional service. For example, in 2018, he was the chair of the topical group on fuel body system and multiparticle dynamics of the American Physical Society. His research interests include lattice-effective field theory, nuclear structure from first principles, ab initio scattering and inelastic reactions, properties of nuclei, quantum computing algorithm for nuclear many-body problems, and many other things. And today he will be talking about nuclear lattice simulations. And with that, I'll give the microphone to Dean.
Thanks so much, Igor. It's a pleasure to be here, and I appreciate you running this, even though you have to give yourself a talk and not too far from now. So thank you, Igor. And thank you, everybody, for tuning in. So today I'll be talking to you about nuclear lattice simulations. And so this is work done with, you'll see a lot of the people involved in what we call the Nuclear Lattice Effective Field Theory collaboration. So here's an outline of what I will speak about today. I'll first give an overview of what is lattice effective field theory. Then I will start with a tale of two interactions that seem similar but actually have very different physics, and try to understand why. Then I'll talk about some symmetries of the nucleonic interactions, the interactions of protons and neutrons that are hidden, but actually have an underlying symmetry if you look carefully. Then I'll speak to you about the core elements of nuclear binding. What is the simplest possible nuclear interaction that would give the bulk properties of the binding of nuclei correctly? Then I'll switch to nuclear thermodynamics, some calculations of the liquid gas critical point in symmetric nuclear matter. Then I will finish with a technique that we call wave function matching for doing calculations of difficult Hamiltonians that are not so amenable to simulations with Monte Carlo simulations. Okay. All right, so let's get started. So lattice effective field theory is a bit different from lattice QCD in that we put protons and neutrons on the lattice as point particles so that we do not resolve the internal structure of the protons and neutrons, but we look at the long distance physics, if you like, with a lattice spacing of between 0.5 to 2 Fermi. And so what we're trying to understand is the low energy physics of these systems. So we're looking at the structure of nuclei, we're looking at superfluidity, and lots of other things like liquid gas transitions, inelastic reactions, scattering, things like that. So here are a couple of review articles that, if you're interested more of the details, there's a now a relatively old review I wrote in 2009, and there's a Springer lecture notes textbook written by my collaborators Timo Lede and Wolf Meissner. So what can lattice effective field theory do? Well, by changing the degrees of freedom from quarks and gluons to protons and neutrons, you actually can take advantage of some symmetries, and I'll talk about that quite a bit today. In particular, there is an approximate symmetry of low energy nuclear physics, where you consider the protons spin up, the protons spin down, the neutrons spin up, and neutrons spin down. Those four are the components of the 4 degrees of freedom of the nucleons. And there's an approximate SU4 symmetry that the low energy interactions respects. It's not exact, of course, but it's approximate. And that's enough to be able to do Monte Carlo simulations without a horrible sign problem. And so this is why we're able to do then calculations in this region of the phase diagram. So here's the density of nucleons per cubic Fermi, and here's the temperature in megaelectron volts. So lattice QCD can do this region up to essentially arbitrary temperatures, okay? But there's some angle here beyond which it becomes difficult to do simulations because of the complex representation of S23, right? And so you have these complex phases in your simulations when you have a finite chemical potential, a non-zero chemical potential. Now, when you switch to nucleonic degrees of freedom, you actually can go to larger densities at colder temperatures because of the symmetry and because you're not resolving all the possible degrees of freedom in the system, okay? Only the ones that are relevant at low energies. Now, of course, there's a maximum density you cannot go beyond. So here's, for example, the density of nucleons in iron, the nuclear matter density. And so using these effective degrees of freedom, you cannot go too far beyond that density, because then at some point you're going to have to deal with the quarks and the gluons. And similarly, there's a maximum temperature beyond which you should not go, maybe about 40 MeV or something like that, right? For the same reason, because you would like to use the microscopic degrees of freedoms of the quarks and gluons. Okay, but in between, so in this region here, there's this region where you can study things like liquid gas transitions, neutron superfluidity, perhaps even a little bit of nuclear superfluidity involving protons as well. Now, there's also a nice overlap region where you can do calculations with lattice QCD and see if you can match with lattice effective field theory. All right. Let me pause and ask if there are any questions at this point.
I don't think there were any raised hands yet.
Oh, okay. Okay, very good. Let's go on. Then the formalism that we're going to use is Chiro-Effective Field Theory. And so this was first put forth by Steve Weinberg about 31 years ago now. So the idea is we construct an effective potential order by order. So we have the nucleons, and so we have some effective interaction. So what we're going to do is we're going to think about what are the important interactions at low energies. That's the idea of effective field theory. So we're going to do an expansion in powers of momentum of the particles. And at the same time, and this is where the word chiro comes in, we count the powers of the pion mass in the same way as we count the powers of the momentum. Okay, so at leading order, or a Q, let's say, is a power of momentum or a power of the pion mass. Then at order Q to the 0th power, we have our leading order interactions. And so we have the exchange of one pion, and we have two S-wave or zero angular momentum contact interactions, two independent contact interactions that you can get due to anti-symmetrization. And then that's what you have at leading order. But then when you go to next to leading order, that starts at order Q squared. You get things like the exchange of two pions and more complicated interactions that would depend on the momenta of the particles. Okay. So what do we do here is, what do we do with these interactions? These are unknown interactions that actually depend on the lattice spacing. So we're putting this on a lattice now. We're putting these Chiro-Effective Field Theories on a lattice. So there are unknown coefficients for these short-range interactions. And what we do is we tune them to reproduce the scattering phase shifts that you see in the laboratory. So here are the scattering phase shifts, the spin singlet S-wave phase shifts. So what I'm plotting here are bands for the calculations we have at next to leading order, next to next leading order, next to next to next leading order. And this is in comparison with the partial wave analysis, okay, of the empirical data. So that's the solid lines. So the diamonds are just showing you the nth real results without the bands. Okay, and so you can see we can get a pretty good reproduction of the empirical phase shifts using these lattice interactions. Here we're using a lattice spacing of 1.3 Fermi. If we change the lattice spacing to let's say 0.99 Fermi, we get a better representation. The lattice artifacts are smaller. And so this is, in essence, how we do the calculations, okay? We tune up these interactions on the lattice, and then we go to the many-body system to do these Monte Carlo simulations. All right. So how do we do these Monte Carlo simulations? Well, the technique we use is, well, this thing called Euclidean time projection. So Euclidean time projection is the idea that you do exponential of minus h tau. And so this is not the real time evolution, but what's called the Euclidean time evolution. And the reason this is useful is that if I have a low energy eigenstate of h here, then it will have the slowest exponential damping from this exponential minus h tau. So the lowest energy states survive the longest. Okay, so we start off with some time tau equals to 0 and go to some final tau final, and we do this exponential of minus h tau. So this Hamiltonian contains a kinetic energy term, and that kinetic energy term, so we're working with non-relativistic nucleons here. So that will have the form the kinetic energy minus del squared over 2m with some factors of h bar squared if you want there. Okay, so if you do the exponential of minus del squared over 2 times the mass, tau, this operation is a diffusion operator, okay? And so this diffusion operator as a function of the Euclidean time can be modeled exactly as a random walk. So you can think of having some nucleons that will be, these nucleons will be doing a random walk in space as a function of the Euclidean time parameter, all right? And so that's how we represent or get the amplitude for the kinetic energy, the time evolution of the kinetic energy. But there's also an interaction term in the Hamiltonian. And so we have things like the exchange of pions and some short-range interactions at leading order. So you can think about then we have these nucleons diffusing in space as a function of Euclidean time, and they have these short-range interactions and these longer-range pion exchange interactions, okay? All right, so let me carry on. So the way we do these calculations are using the auxiliary field method. So what we can do is we can write down these exponentials of the interactions that we're trying to deal with, something like the exponential of minus some coupling C over 2, n dagger n, the density squared. So that gives rise to some two-body interaction. But what we'll do is we'll write this, this term, which I can think of as a Gaussian, if I think of n dagger n as a variable. This is a Gaussian function. And I can rewrite this as an integral of another Gaussian function that has a linear shift in the exponent. So you know how to do this integral. The way you do this integral is you complete the quadratic form. So to make this a perfect square, the missing term is exactly this term here. Okay. So if I were to do this integral over ds, I would get a factor square root of 2 pi, which would cancel this 1 over square root of 2 pi. And the result of the integral would be exactly the exponential minus c over 2 n dagger n squared. The reason why the second line is more is actually quite useful compared to the first line is I no longer have n dagger n squared. So I have now, instead of a two-body interaction, I have a one-body interaction. All right. So my nucleons are interacting with this auxiliary field. Now, the idea is that we put this auxiliary field at every point, we put a different auxiliary field at every point in space and time. So now we have then a random background of Gaussian auxiliary fields that are fluctuating, and each nucleon is interacting with these auxiliary fields at these lattice sites. They're not directly interacting with each other anymore. So we've essentially removed the interaction between the nucleons and replaced it with the interactions of each nucleon with a background field. But of course now, if we then sample over all possible configurations of the auxiliary fields, we get exactly the interactions induced by these auxiliary fields as we had before. So this is kind of how the simulation now looks. Instead of having the interactions of the nucleons with each other, each nucleon will just feel the background auxiliary field. So here's an auxiliary field that does not depend, for example, on isospin, but maybe here we have an interaction that does depend on isospin with some index I here. Now, in this way of looking at things, the pions act very much like auxiliary fields, except for the pions can carry some information across space. So these can give you some non-local correlations, so that you can have some spatial correlations through the pion exchanges. Okay. So now the formalism for these auxiliary fields is quite simple. We have an amplitude for some initial nucleon J, some final nucleon I, and then we have this matrix Gij, and it's a function of the auxiliary fields S and Si, and the pion field. Okay. To get the full amplitude, not just the single nucleon amplitude, we need to multiply all of the amplitudes together for the let's say we have A nucleons, then we have this A by A matrix, and then we have to multiply these guys together and anti-symmetrize because the nucleons are fermions. And so what you get as a result is the determinant of this matrix of single nucleon amplitudes. Okay, so what we do in these nuclear lattice simulations then is to calculate these determinants for every possible configuration of the auxiliary fields and the pion fields. Now, one thing I should mention is that if I have a nucleon with if I have a nucleus with A nucleons, then this matrix is just an A by A matrix. So this is a much smaller matrix than, for example, what you would typically have in lattice QCD, where this would be typically something like L to the fourth or so size matrices, L to the fourth by L to the fourth. Okay. Let me pause and ask if there are any questions, or if anybody has a question, either just unmute or just go ahead and write something into the chat.
I don't think there were any questions so far. I did ask people to put them in chat if there is something.
Great.
But since you already interrupted, I do want to ask a question. The big difference between this auxiliary, so-called Haber-Stokomanovich field, and the pion field, of course, that the S field is really local and pion is non-local. Can you combine them into a single field that has somewhat more complicated structure and just be done with it?
If they have the same quantum numbers, then you can do that. You can put them together. That's correct. Yeah. Okay. So let me now tell you a tale of two interactions. So this story goes back 5 years. We were playing around with two different leading order interactions, which I'll just call A and B, and they were pretty much the same. They had, in essence, in some partial ways, they had exactly the same nucleon-nucleon phase shifts. And they also, in the other partial ways, they were close, but not exact, because they weren't really exactly related to each other. And we also had similar properties for the 3 and the 4 body system. So the triton, helium-3, and the alpha particle, the binding energies were essentially the same. However, when we took a look at the difference between A and B at leading order, and let's say with the Coulomb interaction turned on, what you'd find is when you go to 8, 12, 16, and 20 particles, that B was doing a pretty good job of reproducing the experimental binding energies, but A did not do well at all. Okay, they're very different. All right. So we were actually kind of curious about what was wrong with A, because B we sort of expected, but we kind of expected A to be similar to B. So we took a look more carefully at A in a funny way. What we did was we turned off the Coulomb interaction and then measured the binding energy of the beryllium-8, the carbon-12, the oxygen-16, the neon-20. And then we took the ratio of beryllium-8 to the alpha particle without the Coulomb and got 1.997 with an error of 0.006. Then we took the ratio of carbon-12 to the alpha particle and got 3.00 with an error of 0.01. For oxygen-16 to alpha particle was 4.00 plus or minus 0.02. And then for neon-20, it was 5.03 plus or minus 0.03. So you can see a very simple pattern here with these ratios. We get 2, 3, 4, 5. So you can then ask the question, what is wrong with A? And we realized what had happened with A is we accidentally produced a Bose-Einstein condensate of alpha particles. So mind you, this was not what we're trying to do. We were just playing around with different interactions, different sort of what we call local versus non-local interactions. And I will quantify this now in a moment. Well, I'll quantify it now. So the term local, when we talk about nucleon-nucleon interactions, we mean something like the Coulomb interaction, in that it's just a function of positions. It's a potential energy, okay? So it doesn't move particles around. It's not dependent on the velocity of particles. But you can have a more complicated interaction that's velocity dependent. And these are what we call non-local interactions. So if you write this sort of generally in position space, you can think of the local interactions as being diagonal in position space, and the non-local interactions as being having the off-diagonal terms where the particles can move their positions, but the center of mass remains the same, okay? And so the difference between A and B is that A had pretty much, except for one pion exchange, A had only non-local interactions, okay? This velocity-dependent sort of off-diagonal in space interaction, where B had a significant amount of local interactions, like the Coulomb interaction, you know, where it's diagonal in space. So somehow, by changing from one to the other, by removing the local interaction and going to the non-local interaction, there was no damage to the phase shifts. The nucleonuclein interactions were fine. The phase shifts look good. The three-body system looks good. For the tritron, the helium-3, the four-body system looks good, but now once we get to the larger system, things look bad. Something has happened to the interactions between the alpha particles. Somehow, to make a Bose-Einstein condensate, what you need is for the alpha particles is to essentially be not talking to each other. The interactions have essentially gone to zero. And so we actually verified this, that in fact, the alpha-alpha scattering phase shifts are quite a bit different. So when we take the A interaction, so let's start with the B interactions, which are the good ones, with Coulomb added, these are the squares here. We get this for the S-wave phase shifts versus the laboratory energy. It looks something like this, which is right on top of the empirical results. Okay, so it's doing a good job of the alpha-alpha scattering. Right. Now, if we do the same calculation for the interaction A, then we get something like this, and you see it's much smaller. It's essentially zero on average. It's attractive here, but then it's repulsive here. So it seems that by taking these interactions to be non-local for the nucleon-nucleon interaction, we actually have diminished the sort of, if you want, the van der Waals sort of induced interaction between the alpha particles. And this is a really an unexpected thing to happen. Now, some of you might have questions on how exactly we do this alpha-alpha scattering calculation. This is a whole other talk, so I'm not going to spend time on that. But basically, we have a paper on that using something called the adiabatic projection method to do these calculations. It's quite involved, though. Okay. Now, so knowing that there's this difference, this sensitivity to the locality versus non-locality, as well as the sensitivity to the range of the nucleon-nucleon interaction itself, we can in fact probe this quantum phase transition. So we can take, for example, a linear combination of the interactions for A and for B, and when lambda, so let's say lambda is this parameter that interpolates between A and B, then over here on the A side, we have this alpha particle gas, a Bose-Einstein condensate. Over here, we have a nuclear liquid where everything sticks together for symmetric matter. And then there's this phase transition here, a quantum phase transition, where when we have enough particles, enough nucleons, turning off the Coulomb interaction, I should mention. Here, we're turning off the Coulomb interaction. We form a droplet with an arbitrarily large number of these nucleons. But if we go a little bit further along, we then also form stable finite droplets as well. Okay, so this is our understanding of the fact that nuclear physics seems to sit close to a quantum phase transition. Now, let me pause in this. Well, if there are any questions, just go ahead and write them into the chat. So I won't keep pausing. I'll keep going. So let me now tell you a little bit about the symmetries of the nucleon-nucleon interactions. So there are some papers that have studied the large NC limit of the nucleon-nucleon interaction. So when we take the number of colors to NC to be odd and large, then the nucleons become heavy, all right? And sorry, so then, yeah, that's actually right. Then you have many quarks and the nucleons become heavy. And the quarks essentially can be thought of in some sort of mean field kind of a sense. You can think of the wave functions of the quarks. And what happens is that there's a symmetry that emerges in that the spin of the nucleon and the isospin of the nucleon can be interchanged from one to the other. What happens is that in the large NC limit, the wave function that you get for the spin dependence and the isospin dependence are identical. Okay, and so that actually shows up in the leading large NC interaction between the nucleons. So this is what's called the central interaction, which is independent of spin and isospin. And then you have this spin isospin exchange interaction where you have spin.spin for the two nucleons, and you have the tau.tau for the two isospins of the nucleons, and multiplying by some other central potential W. Okay, and then you have a tensor force interaction where you have a tau.tau, and you have then this tensor force interaction. The thing that I want to emphasize here is that in the large NC limit, what happens is that every time you have a spin polyspin matrix, you have to have a isospin matrix at the same time. So you see the sigma here goes with the tau, the sigma here goes with the tau. Right? Now, this term here is what you would say is SU4 symmetric. I talked about this earlier, that it's independent of spin and isospin. So you can think of rotating the proton up, proton down, neutron up and neutron down amongst each other. And this term here is not SU4 symmetric, but there's a spin-isospin exchange symmetry where you essentially flip spin with isospin. You can think of taking a neutron spin up and exchanging it with this proton spin down, and that's essentially exchanging spin with isospin. Right? Now, this term, however, is a tensor force, and this sort of screws everything up. But it turns out now, if you look at this tensor force, if you were to average over all spin configurations, if you had some way of averaging over the spin configurations while keeping everything else fixed, then this tensor force averages to 0. And so you can take advantage of this fact. You can do things like take a look at the S-wave phase shifts. Okay, for the spin singlet, here's the spin singlet, and here's the spin triplet phase shift. But now, if you block the tensor force by projecting onto the L equals 0 partial wave only, so that you don't have the coupling to the L equals to 2, the D wave, then what you find is pretty miraculously, you get something very similar to these spin singlet phase shifts. So there's this hidden symmetry in the nucleon-nucleon interactions that was just hiding there to be seen if you can block out the force, the effect of the tensor force. You can see it even more strongly for the D waves. So here's the spin singlet D wave, okay? And here are the spin triplet D waves in the various partial wave channels, okay? The 3D1 here with the stars, the 3D2 here, okay, and the 3D3, sorry, 3D2 and 3D3. Okay, but now if you average them all together by averaging over all of the spin components, then you get this average triplet D wave, and you can see it's lying right very similar to the 1D2, the spin singlet D wave. Okay, so in this paper here, we worked out the consequences of this and the predictions you can make for not just the two nucleon interaction, but actually the three nucleon sector, because much less is known about the short range interactions for the three nucleon force in Chiro-Effective field theory. Once you go beyond the next to next leading order, there's a lot of terms that come out, and knowing that there's this underlying large NC symmetry actually helps you figure out that these terms should be stronger than the others because of large NC counting. Okay. All right. Again, if you have any questions, go ahead, put them in the chat. Otherwise, I'll move on. So the next topic, yeah.
I guess since you asked, what is the physical reasoning for, I mean, isospin, I imagine, is like an exchange interaction, right?
So yeah, the protons and neutrons are like the up and the down components of the nucleon.
What is the physical reasoning that spin and isospin can be exchanged like this?
Yeah, so it comes from this point. So the argument, so let me give you a little bit of the derivation of the large NC here, okay? So let's suppose we just had an operator that was something like Q bar Q, okay? Q bar Q would count the number of quarks. If you then take Q bar Q and act upon a nucleon, or either a neutron or proton, you would count the number of quarks, so it would be proportional to NC, all right? Right? Now, similarly, if I have an operator that was something like Q bars sigma tau Q, that would have a spin and an isospin degree of freedom, okay? Then I would also have something generically that would scale with the number of quarks, so it would be of order NC, okay? But if I have an operator that was just Q bar sigma Q, then that is actually going to count the spin of the nucleon, which is 1/2. So it's actually suppressed by a factor of 1 over NC compared to the other operators. The same thing for the Q bar tau for the isospin Q, okay? This will be isospin 1/2, and so it's also suppressed. So that's why there's this symmetry coming out that every time you have a sigma, you have to have a tau with it. And that is what leads to this exchange symmetry. Now, the tensor force screws this up because the sigmas can couple to another spatial vector like the position vector. But if you can remove this effect by spin averaging, this is when the symmetry appears. Okay.
Okay.
Yeah.
Okay. Thanks.
I think there's a question by Oleg.
Yes, actually, I have a somehow related question.
Yeah.
And concerning this interesting spin-isospin symmetry, can one expect something expressed on quark level? Because it's actually quarks are used in your argument.
Yeah, exactly.
I mean some just empirical observation.
Yeah. So the isospin exchange symmetry can be seen in the ground state wave function of the nucleon. The fact that the spin and the isospin, I can exchange them, right? So essentially, if you take the up quark with spin down and exchange it with the down quark with spin up, that's essentially, if you flip those, that's essentially exchanging the spin degrees of freedom with the isospin degrees of freedom.
Because what came now to my mind, there is empirical observation that difference of U and D valence quark distributions is similar to polarized U quark distribution. So difference of spin and isospin projection. The isospin projection is close to difference of spin projection. Maybe this property can be a sort of explanation of that.
Yeah, that would be really interesting. I'd be happy to discuss this with you.
Yeah, because it's old observation in quark models that indeed it is so. So, and actually then I learned, I thought about something like instantons, but what you presented here looks maybe more feasible in this sense.
One thing that one thing that we discussed in this paper is the breaking of this argument, though. If the nucleons are in a moving frame, then the Pauli-Lubansky tensor is different from just what you have in the rest frame.
This is
and so then this argument breaks down. So if the nucleons are colliding with too much energy, then this no longer holds.
Well, but of course this is some just not exact relation, but for pattern distribution it's a sort of similarity. So maybe some similarity remains. Well, thank you.
Sure. Very good question. Okay. All right, so now let me tell you about, since we've talked about these symmetries, we can ask the question, what are the essential elements for nuclear binding? So we said there's this spin-isospin exchange symmetry. Let's suppose we don't really want to resolve all the different spin orbit splittings of the nuclei, and we just want to get the average bulk properties of nuclei right. How simple can the interaction be? And so that's what we did in this project here. What is the minimal nuclear interaction that can reproduce the ground state properties of light nuclei, medium mass nuclei, neutron matter simultaneously with no more than a few % error in the energies and charge radii? Okay, so we constructed an interaction with only 4 parameters. Okay, so in the spirit of what we were just discussing, that the spin triplet and spin singlet S waves are similar to each other, we just have one interaction for both S wave channels. So there's the strength of the S wave 2 nucleon interaction, there's the range of the 2 nucleon interaction, and there's the strength of the 3 nucleon interaction. So these three parameters we can tune simply to the 2-body system and the 3-body system. So these are all fixed by the 2 and the 3-body systems. Then there's one extra parameter, which is the range of the local part of the 2 nucleon interaction. So remember, when I mean local means that it's like the Coulomb interaction. that the interaction is diagonal in position space. It's not velocity dependent or anything. And so, surprisingly, with this one extra parameter, you can reproduce essentially the binding energies of over 80 nuclei as a result. Okay, so here are the lattice results in the solid symbols for different isotopes of hydrogen, helium, beryllium, carbon, oxygen, neon, magnesium, silicon, sulfur, argon, and calcium with experimental data. And so you can see it's qualitatively giving everything right. There's, of course, a lot of things missing, in particular the spin-orbit couplings that are quite important. You can see are not being reproduced perfectly here. In fact, not reproduced at all in some sense, but still the bulk properties are correct here. Okay, suggesting that the core essence of nuclear binding is as simple as what we've written down. So let me then go on. I can show you the quality of the reproduction. So here is the binding energy for the tritone helium-3 compared with experiment. So this is fit. So that's not too surprising. But now then, for helium-4, you're doing pretty well with experiment. Oxygen-16, also pretty good. Neon-20, also good. Magnesium-24, silicon-28, calcium-40. And also the charge radii are in units of Fermi. So these were in units of MeV. These are charge radii in units of Fermi, are also pretty well reproducing the experimental values. Okay, so that suggests to you that this analysis is actually correct, that the binding mechanism of the nucleons is relatively straightforward. Now, in order to be able to see more than just like the charge radius and measure the binding energies, we need to be able to see where the nucleons are. And for this, we developed something that we call the Pinhole Algorithm. Okay, so let me tell you how the Pinhole Algorithm works. So we're just going to work with these density operators. So a density operator, rho I, comma j for spin I and isospin j. So just A dagger A for that spin and isospin. And rather than going through this equation, I'm just going to just show you with pictures what's going on here. What we have are these little pinholes, which are these density operators here. And this is essentially like a brick wall. And the amplitude will die if a nucleon hits the brick wall. It will only be non-zero if it passes through the little pinhole that has a given spin and a given isospin. So we do the simulations with these pinholes, and we use Monte Carlo, Metropolis Monte Carlo updates to update the positions of these pinholes. And what this does for us is it gives us then a classical distribution of where all the nucleons are. And so if you want more details about this, you can read it in this paper from 2017. So from this simulation, we actually then can get a very nice classical distribution of where all the particles are. And so then we can give you a charge density profile as a function of radial distance for oxygen-16. Here at leading order is in the red with the circles, and then with the Coulomb included by perturbation theory in the blue squares, you can see it's doing a pretty good job of reproducing the empirical results, even though this interaction, I should mention, is extraordinarily simple. But it's still doing a pretty good job. You can see for calcium-40, it's not quite as accurate, but it's actually still quite good. Okay, so let me now go on. Now, having developed this pinhole algorithm, we realized that we could use this to do thermodynamics. So we started doing ab initio nuclear thermodynamics with something that's what we call the pinhole trace algorithm. So if you want to learn more about this, this is from a paper from 2020. So for nuclear thermodynamics, what we want to do is calculate the trace of the exponential minus beta h. So we'll be talking about the canonical ensemble, where the number of nucleons is fixed here. But we have now actually done also the grand canonical version of this. Sometimes you want to do the grand canonical as well. So that's possible. But let me speak about the canonical ensemble. Okay. So let me show you again, but with using pictures. So for the pinhole trace algorithm, what we do is we have pinholes at the beginning time step, and we have pinholes at the last time step. And the pinholes in the beginning and at the end are exactly the same. So you can think of this as just summing over position eigenstates. So position eigenstates give you a complete basis. So what we're doing is we're doing a trace of the of the exponential minus beta h with respect to the basis elements in position space. So that's what the pinhole trace algorithm does for you. All right. And so by doing this, we can then see the charge density profile of oxygen 16 as a function of the temperature in our simulation. So we put oxygen 16 in a box. This box is about 18 Fermi in length, 18 by 18 by 18. And we then do the simulation. So at 0 temperature, we get essentially what we had before. And then we turn on the temperature. And what you can see is that there's a tail that's forming that's caused by the nucleons that are boiling off the oxygen 16 nucleus. All right. And you can see the central density is also decreasing like this. You get this very nice tail that extends throughout the whole box. Okay. All right. So then what we did was we tried to take a look at the phase diagram of symmetric nuclear matter. So here's symmetric nuclear matter. So this is rho over rho 0, where rho 0 is nuclear matter density, the density of nucleons in iron. Okay. And so here's the critical point. So this is the temperature in units of MeV. This is just a schematic diagram of what we think it should look like. And so you can see here, way up here, this is not something we can access, but if you're doing lattice QCD, you'd be interested in the quark-gluon plasma of this critical point here. All right. So we're interested, though, in this critical point for the liquid vapor transition. Okay. And so we did some calculations using the pinhole trace algorithm. Again, you can find more details in our paper from 2020. Where we calculated the chemical, we plotted as a function of the nucleon density rho over rho 0. The chemical potential is plotted here. So this is for the curve for 10 MeV temperature. This is for 11 MeV temperature, for 12 MeV temperature. Okay. And so this is what's being plotted is the liquid vapor coexistence line. And this point right here, this thing here is the liquid vapor coexistence line. I was pointing to the wrong thing. Okay. And this point here is the critical point. All right. And we can also calculate the pressure. So the pressure versus the reduced density. Same sort of a sketch here, 10 MeV in temperature, 11 MeV in temperature. Here's the liquid vapor coexistence line, and here's the critical point. And so here is the empirically measured critical point from heavy ion collisions, low energy heavy ion collisions. And so here are the properties we calculated. The critical temperature is around about 16 MeV. The critical density is about 0.09 nucleons per cubic Fermi. And the critical chemical potential is minus 22 MeV. And the critical pressure is about 0.26 MeV per cubic Fermi. Okay. Now, we also were interested in alpha clusters. To what extent you can see alpha clusters in symmetric nuclear matter as a function of density and pressure. So what I'm plotting here is rho to the 4th expectation value divided by the expectation value of rho raised to the 4th power. Okay, so this guy is just the nucleon density raised to the 4th power, but this is in some sense the short-range correlation measurement for 4 nucleons being on the same lattice site. It's like a 4-nucleon contact, if you know what the notion of a contact is. If you don't, it's just basically just a 4-body operator on a given lattice site. Okay. So what we see here is that when we're above the critical temperature, this measure of alpha clustering, if you'd like, is flat. So it doesn't seem to change with the temperature. Okay, so if we're at the critical density or above, it doesn't seem to change very much. But now, if we are at below the critical density, we see that this rho to the 4th is actually much higher. Okay, especially at low temperatures, but it decreases as a function of temperature. So what we see here is that below the critical temperature, we have alpha clustering at low temperatures, but we can actually change that degree of alpha clustering as a function of temperature. So that's something we want to try to understand a little bit better. Okay. Now, let me then switch to my last topic. So this is something that's in progress, but we're actually very excited about this because, to be honest with you, this is something I thought that was not going to be possible, but it turned out that it actually worked. So this is what we call wave function matching. So here is just to try to give you an analogy here. Here's the Mona Lisa, of course, and here's my cat. Okay, and so the idea of wave function matching is to take a Hamiltonian that you want to simulate and a Hamiltonian that you can simulate, and to make them closer to each other. So I'm just sort of showing you, I've taken my cat's head here and put it on the Mona Lisa. That's kind of what wave function matching is all about, right? This is work in progress right now. There should be a paper on the archive perhaps in the next couple months. So let me try to explain the problem. So lattice Monte Carlo simulations can compute highly non-trivial correlations in nuclear many-body systems, but sign oscillations prevent us from doing direct calculations with sort of these high-fidelity Hamiltonians, like an next to leading order Hamiltonian would probably have a sign problem that would be difficult to manage. And this is coming from these short-range repulsion interactions that are difficult with auxiliary field Monte Carlo. Now, wave function matching solves this problem by means of unitary transformations in perturbation theory. Okay, so how does this work? By using the unitary transformations, we construct a high fidelity Hamiltonian that can be reached by perturbation theory, even just first order perturbation theory, starting from a Hamiltonian without a sign problem. So that may not be clear what I'm trying to convey here. So let me show you with the diagram. Suppose here's a set of all Hamiltonians that we can compute non-perturbatively efficiently with our lattice simulations. But let's say the Hamiltonian that you want to try to describe is this Hamiltonian HA over here. And perturbation theory won't work because this is too far away from any Hamiltonian that we can simulate non-perturbatively. Right? But what we can do is we can consider the set of all unitarily equivalent Hamiltonians that would be equivalent to HA. All right? In other words, they would produce the same phase shifts. They would only differ in the finite distance behavior, the short-range behavior of the Hamiltonians. So in some sense, there's no difference between any other Hamiltonian on this circle here, on this sort of orbit, the unitary orbit here. So the idea then is to just simply take a different Hamiltonian, HA prime, that is close to a non-perturbatively computable Hamiltonian, and then use perturbation theory. All right. So that's the idea of wave function matching. Let me try to show you with an example. Suppose we have an interaction VA, which is just a local interaction on the lattice. So it has a repulsion at 0 lattice units. And so this is 1 lattice unit, square root of 2 lattice units, and square root of 3 lattice units, by the way, if you're trying to figure out what this is, why the spacing's like this. Okay. And so there's a repulsion here. There's a strong repulsion, and then there's some attraction over here. But let's suppose we have some other interaction, VB. This is what we want to calculate. This is something we can easily calculate because we can do this with auxiliary fields because it's attractive and it doesn't have this repulsion, right? So how can we try to deal with this interaction here? So let me just show you that these interactions are actually quite different from their phase shifts. Okay, so here are the S-wave phase shifts as a function of momentum for VA. So you can see it actually goes to 0 at about 260 or 70 MeV momentum, and it becomes negative, telling you we have some repulsion at high energies. Now, at high energies VB, it never goes to 0. It remains positive, telling you that we have attraction at high energies, high momentum. Okay, so they're not very similar to each other. They're quite different. So this causes a problem. So let me now just keep going, though. Let's write the eigenenergies and the eigenfunction, the wave functions for the two interactions as follows. So HA and HB. So psi A and the excitation will be labeled with N. And so K will be my kinetic energy. VA is my interaction. So my energies will be EA labeled by N for the eigenstate, the nth eigenstate. Okay, so I have EA for N for the A interactions and EBN for the B interactions, and I'll call them psi AN and psi BN. So we would like to compute the eigenenergies of HA. Let's say HA is what we really want to deal with, but it's a difficult interaction because it has this hard repulsion. Okay, we really want to calculate the eigenenergies of HA, but we're going to start from the eigenenergy of H, the eigenfunctions of HB, because they are what we can compute non-perturbatively, and then we'll use first order perturbation theory. So we're going to do something like this. We're going to take here are the exact eigenenergies of EA, for HA, sorry. And I'm going to just take the eigenstates of HB and compute the expectation values of HA. This is essentially just doing first order perturbation theory. And what you can see is it's terrible. Instead of getting minus 1.2, we get 3.0 instead of 0.2. So these are scattering states, so they're much smaller. These are low energy scattering states. This is still not good because it's off by 50% or so. All right, so these are not good at all. However, what we can do is the following. Let's define a projection operator, P, that is just going to cut out the piece of the two nucleon sector, such where the nucleons are separated by a distance r, small r, that's less than capital R. So this is just a projection operator onto the two nucleon sector, where the two nucleons are less than a distance capital R from each other. Now what I'm going to do is I'm going to define a unitary transformation such that the piece, so this here, P acting on psi 0a. So psi 0a is the ground state of Hamiltonian A, and this is the projection operator, the short distance projection operator. So this is the piece of the wave function, of the ground state wave function that's at short distances. And I'm going to divide by the norm of this piece to make this normalized. And I'm going to make the unitary operator map this to the short distance piece of the ground state for interaction B, divided by its norm, okay? So this is then one piece of the unitary transformation. There are many possible choices for U, and I'm not going to talk about all the different possibilities, but the key step is to make this mapping such that the short distance part of psi ground state of A is mapped to the ground state of B, the short distance part. And then I'm going to take this unitary transformation and define H prime of A as just the unitary transformation of HA. And then now I'll define the interaction, the new interaction V prime of A, as just HA prime minus the kinetic energy, because the kinetic energy is not part of the interaction, of course. And so this will define my new interaction VA prime. And so now what I can do is I can ask, what do the phase shifts look like? Well, the phase shifts are exactly the same as the phase shifts for VA. VA prime is unitarily connected to VA, right? HA prime is unitarily equivalent to HA, and VA prime, when I add the kinetic energy to it, gives me HA prime, okay? All right, but now let's see what's happening to the wave functions. What am I doing? I'm taking, so let's suppose this is the wave function for, psi A, the ground state, with this hardcore repulsion, so it goes to 0 here. But here's the wave function for psi B. What I've done is essentially surgery. I've essentially transplanted the short distance part of psi B to psi A, to make psi A prime. So there's a little bit of a kink here, okay? The rest of the wave function is just psi A. Okay, but the first part is just copying with a normalization factor the wave function for psi B. So the idea is to make this the ground state of psi A prime look like the ground state of psi. Okay, to make it similar at short distance to psi B. All right, but is unitarily equivalent. The HA prime is unitarily equivalent to HA. So that's the game we're playing. Let's see how well it works. So if we take capital R for the short distance projection to be 1.3 Fermis, then we see it's doing much better. So now with first order perturbation theory, we get within 0.7 MeV of the exact ground state. Okay, and these guys for the scattering states are also quite good. You can see it's a vast improvement over not using this wave function matching trick. These guys are way off compared to these, where these are pretty close. Now we can do much better if we extend R a little bit further to 2.6. Then you can see that we're actually doing quite well with first order perturbation theory. Okay, so this is the idea of wave function matching. We have now applied this to all of the chiral interactions up to M300. It works beautifully. So I'm just going to show you the case for the 3s1 3d1 channel. Okay, so here are the phase shifts for the 3s1 and the triple G waves. They're coupled together, and here's the mixing angle that you have between the two. And so here's an example of this. You can see the L equals 0 wave function, ground state wave function for psi A, okay, and for psi B, And then this is the D, these are the D wave functions for psi A and for psi B. And so we're doing this surgery where we're replacing the short distance part of A with the short distance part of B up to a normalization factor. And so what you can see now is if we don't use wave function matching, perturbation theory is terrible, 0.91 instead of minus 2.22. But with a wave function matching with first order perturbation theory, we're only off by 0.08 MeV, about 80 keV. Okay. And so that's what we're doing with this wave function matching thing. We're using it for all of our calculations now. So now let me summarize. So we began with an introduction to lattice effective field theory. Then we presented evidence that nature is close to quantum phase transition between nuclear liquid and Bose gas of alpha particles. Then we discussed the hidden spin isospin symmetry of the nucleonic interactions that can be derived in the large NC limit. And then we constructed a minimal nuclear interaction that can reproduce the ground state properties of light nuclei, medium mass nuclei, as well as a neutron matter. I didn't show you the neutron matter results, but it works just as well. We presented first principles of calculations of nuclear thermodynamics using what's called the pinhole trace algorithm. And then we looked at the nuclear liquid vapor or liquid gas phase diagram and alpha clustering as a function of density and temperature. And then we wrapped up by introducing this wave function matching method. By using unitary transformations, we can construct a high fidelity Hamiltonian that can be reached by perturbation theory from a Hamiltonian without a sign problem. So thank you very much for your attention. And if there are any questions, I'd be very happy to answer.
Okay. Thank you very much for this great talk. For those, I'm subbing for Igor. He had another sudden commitment, unfortunately. So, any questions, Oleg?
Thanks for interesting talk, and I have a couple of probably naive questions.
Sure.
And first, is it possible to get the Hoyle state for carbon, which is crucial for nucleosynthesis? And second question, is it possible to consider heavy nuclei, even super heavy?
Yeah. So the Hoyle state, we've been doing this for many years. Yeah, the Hoyle state comes very easily in the lattice EFT approach. Yeah. In fact, we are working now to use this wave function matching to hopefully really resolve the structure of the Hoyle state. So we've had several papers on it, but there's still some controversy over the details geometry of the alpha clusters. And we hope to have this completely resolved in the next couple of years. Now your question about the super heavy. So the super heavy, in principle, yes, we can do that. The difficulty we will have is that the Coulomb interaction becomes very important. And so in order to deal with the Coulomb interaction, this again causes a sign problem. But we have a technique for dealing with that, which is what's called Eigenvector Continuation. Okay, and so if you just Google Eigenvector Continuation, you'll see a bunch of papers on this technique for how to deal with some interaction that's non-perturbative using a technique that looks a bit like perturbation theory, though.
If I can just continue concerning Hoyle state, what is your general conclusion? Is it really a sort of fine-tuning required to get a Hoyle state, or it is more just probable or just something common? So should we be very happy to have Hoyle state because first it appears as anthropic argument? What is your, can you get some general conclusion on that?
Yes, so the jury's out on this, but personally, from what I've seen, there is fine-tuning involved. There's even fine-tuning involved in simply having beryllium 8 be close to the alpha threshold. If you were to change some parameters of nature, you can change this from what I'm seeing. Yeah.
So in this sense, our universe is something special concerning Hoyle state, right?
This is what one could conclude. Yeah.
Okay. Thanks.
Yeah, sure.
Further questions. Wait, was there another one? I have a question actually about, I didn't really understand when you have what was the symmetry that allows you to evade the sign problem? And sort of as a question, how far in chemical potential space can you go? Because there's this recent neutron star evidence that there is a bump in the speed of sound, and it might be related to what is called quark-ionic matter and so on and so forth.
Oh yeah. So if it has to do with quark-ionic matter, then the formalism breaks down, right? So yeah. But to answer your question about the symmetry, it's a pairing symmetries. So I mentioned that in low energy nuclear physics, there's an approximate SU4 symmetry where you have proton spin up, proton spin down, neutron spin up, neutron spin down. So the determinant then, if we have an exact SU4 symmetry, then what happens is that when you put in the auxiliary fields, in the auxiliary field matrix, if you have like the single nucleon matrix, we can think of then the matrices as having a block diagonal form. So we have a block for proton spin up, we have a block for proton spin down, we have a block for neutron spin up and neutron spin down. And so we have 4 copies of this matrix. So when you take the determinant, it's raised to the 4th power. And that's what's blocking the sign problem. Okay. Now, if you now have then, if you have an isospin asymmetric system where you have more neutrons than protons, then you lose the isospin symmetry, where you have more protons than neutrons, but you still have the pairing symmetry, the spin up and spin down pairing symmetry. And so that again will block the sign problem. So any remnant of this pairing symmetry where we have 2 copies of the same blocks, so it's raised to the 2nd power or some even power, this is what gives us the reduction of the sign problem.
Okay, good, thanks.
Sure.
Well, why does the formalism break down if you have quark-ionic matter?
Oh, well, so the idea is we're working with nucleons. And so it's an effective theory. If the nucleons are not the correct degrees of freedom, then it's not going to work.
So for example, like chiral restoration in nuclear matter, partial chiral restoration that you also cannot do.
Yeah, what one could do is one could still try to do the calculations at that particular point in the phase diagram and see if there's some sort of hint at something going wrong. I'm suggesting that there is a phase transition, but we don't have the degrees of freedom to resolve the question of what really does happen.
Okay, thanks. Further questions? Thank you very much for a great talk.